In today's video, we're going to talk about why different planets have completely different types of rain. On our planet, Earth, approximately 505 trillion tons of precipitation fall every year. These rains constantly remind us how perfectly balanced our planet is and how beautiful rainfall can be. During and after every rainfall, breathtaking landscapes emerge all across the globe, yet a large portion of humanity goes through life unaware of these incredible scenes. But while rain on Earth leads to such beauty, what about other planets? On our planet, depending on the amount, rain is generally harmless. However, there are planets out there that experience precipitation far beyond what Earth receives, sometimes in the form of acid, sometimes glass, and sometimes even more extreme substances. So the real question is this: why does every planet have a different type of rain? Even on planets that are structurally very similar to Earth, there can be rainfall so extreme that it turns the environment into something resembling hell. Today, I'm going to explain in detail how planetary climates form and why each planet has its own unique type of rain. Before we begin, don't forget to like the video, subscribe to the channel, and leave a comment with your ideas for future content. If you're ready, let's get started. First of all, thanks to modern technology, we now know that the diversity of precipitation types observed on different planets is not caused solely by differences in atmospheric composition. The type of rainfall that forms on a planet can actually be traced all the way back to its initial formation process. Factors such as its distance from its star, its mass, magnetic field, internal heat, and atmospheric evolution all play critical roles in determining the nature of precipitation on that planet. The reason we have to go this far back is because precipitation is not simply a basic condensation event. Rather, it is the result of complex systems working together, including thermodynamic equilibrium, phase transitions in chemistry, and fluid dynamics. A planet's climate begins to take shape from the initial conditions within the protoplanetary disk. After a star forms, the remaining disk contains regions with different temperature ranges. These temperature differences determine which elements and compounds can condense at specific distances from the star. For example, in regions close to the star, only materials with very high melting and boiling points, such as silicates and metals, can condense. In contrast, in the colder, more distant regions, volatile compounds like water, ice, ammonia, and methane can exist in solid form. This distinction lays the foundation for the fundamental difference between terrestrial planets and gas giants, which we discussed in detail in a previous video. As we know today, terrestrial planets are largely composed of silicates and metals and tend to have relatively thin atmospheres. On the other hand, gas giants possess extremely thick atmospheres, primarily made up of hydrogen and helium, far denser than Earth's atmosphere. However, the key factor that determines the type of rain on a planet is not just the thickness of its atmosphere. The real determining factors are the chemical composition of the atmosphere and its temperature-pressure profile. This profile dictates which compounds can exist in which phase at different layers of the atmosphere. Additionally, for precipitation to occur in any atmosphere, three fundamental conditions must be met. First, there must be a gas capable of condensation. Second, the temperature and pressure conditions must allow that gas to condense. And third, there must be nucleation particles that can initiate the condensation process. On Earth, this process occurs through the water cycle. Water vapor rises into the atmosphere, cools, condenses, and then falls back to the surface as rain. Now here's something fascinating. As far as we currently know, this mechanism follows the same fundamental pattern throughout the entire universe. In other words, every precipitation cycle operates based on this same framework. However, and this is the truly surprising part, while the core mechanism remains the same everywhere, the actual content of what is falling as rain can vary dramatically from one planet to another. For example, if a planet's atmosphere is largely composed of methane, then instead of a water cycle, a methane cycle is observed. In this case, methane evaporates, condenses, and then falls back to the surface as liquid methane rain. If you think such a system cannot be stable, you would be mistaken. As mentioned before, if the right temperature and pressure conditions are present, this kind of system can indeed remain stable. On the other hand, at much higher temperatures, even metal oxides or silicate vapors can condense and form rain. When we look at the atmospheric temperature profile, we see that it depends on the balance between the energy coming from the star and the planet's own internal heat. Radiation from the star heats the upper layers of the atmosphere, while heat coming from within the planet warms the lower layers. The interaction between these two energy sources creates convection currents in the atmosphere. Convection occurs when hot gas rises and cooler gas sinks, and this process plays a critical role in the formation of condensation regions. Of course, what I've described so far generally applies to terrestrial planets. In gas giants, however, However, these processes become much more dramatic due to their ATI thick atmospheres. These atmospheres are so massive that there is no clearly defined boundary that can be described as a surface. Instead, as you go deeper, both pressure and temperature continuously increase. Under these conditions, different compounds can condense at different depths. For example, ammonia clouds may form in the upper layers, water clouds deeper down, and even deeper regions of metallic hydrogen can exist. This means that within a single gas giant, multiple types of rain can occur at different atmospheric layers. In addition, a planet's mass and gravity are also key factors that directly affect precipitation types. Planets with greater mass have stronger gravity, which allows them to hold onto their atmospheres more tightly. As a result, heavier gases that would escape from smaller planets can remain trapped in their atmospheres. Strong gravity also influences the size of raindrops and their falling speed. In denser atmospheres, droplets may fall more slowly and in some cases can reach the surface without completely evaporating. In contrast, atmospheric escape is much more common on low-mass planets. Solar winds and thermal escape processes cause lighter gases to continuously leak into space. Over time, this leads to the thinning of the atmosphere and consequently the weakening of precipitation cycles. One of the best examples of this today is Mars. In the past, Mars had a much thicker atmosphere and most likely possessed liquid water similar to Earth. However, over time, the planet lost much of its atmosphere and has now become an almost completely dry world. In addition, just as important as atmospheric thickness and gravity, perhaps even more important, is the magnetic field, which is one of the key factors in protecting a planet's atmosphere. A planet with a strong magnetic field is shielded from stellar winds, preventing its atmosphere from being stripped away into space. As a result, the planet can maintain a much more stable climate system over the long term. A stable atmosphere is also a crucial requirement for a consistent precipitation cycle. Beyond this, it is important to discuss atmospheric pressure, as it is also a critical factor. As mentioned earlier, high pressure allows gases to condense at higher temperatures. For this reason, the same compounds can form rain at different temperatures on different planets. This also means that phase diagrams must be reinterpreted based on planetary conditions. In conclusion, the type of precipitation on a planet is far more complex than simply what is present. It is the result of an intricate network of physical and chemical interactions. Each planet develops a unique atmospheric structure based on its formation history and evolutionary process. This is the clearest explanation for why every planet has a different type of rainfall. As a result of the parameters discussed, on some planets, continuous evaporation occurs on the day side, while condensation and precipitation take place on the night side. Although this still forms a cycle, it is not a balanced system like on Earth. Instead, it is a one-directional and extreme transport process. For example, on an extremely hot exoplanet, metallic compounds evaporate on the day side and are carried to the night side by powerful winds. There, they condense and fall as liquid metal rain. In such environments, wind speeds can reach kilometers per second, making the horizontal component of precipitation just as important as the vertical one. In this context, one of the most remarkable planets in terms of precipitation is WASP-76b. This planet orbits very close to its star, causing surface temperatures to exceed 2,400 degrees Celsius. These temperatures are so extreme that even metals like iron can vaporize. As a result, iron evaporates on the day side, exists in gaseous form within the atmosphere, and is transported to the night side by strong winds. When temperatures drop on the night side, this iron vapor condenses into liquid droplets. This leads to the formation of what can only be described as iron rain, which then settles into the lower layers of the atmosphere. Planets like this demonstrate just how wide the physical range of the concept of precipitation can be. Another important and fascinating example is the planet HD 189733b. Yes, just like its name, the phenomena occurring on this planet are quite extraordinary. Through spectroscopic analysis, scientists have detected silicate particles in its atmosphere. Under high temperature and pressure conditions, these silicates condense into droplets that are essentially made of glass. This is not a metaphor. These are literally glass droplets. What makes this even more striking is that these glass rains occur at extremely high speeds, and unlike on Earth, they move horizontally. In other words, rain on this planet does not simply fall downward, it becomes a phenomenon that is also violently swept sideways. However, this should not be confused with rain on Earth being blown sideways during storms. On this planet, these particles truly travel horizontally across the surface, behaving like a massive sandblasting glass storm that erodes everything in its path. This is one of the most striking examples of how atmospheric dynamics can fundamentally alter the nature of precipitation. When we move to colder environments, precipitation takes on an entirely different chemical framework. One of the best examples of this can actually be observed relatively close to us within our own solar system. Titan, a moon of Saturn, has a thick atmosphere composed mostly of nitrogen and methane. The surface temperature on Titan is is around minus 180 degrees Celsius. At this temperature, water exists only in a frozen state, while methane and ethane can remain stable as liquids. For this reason, Titan has a methane cycle very similar to Earth's water cycle. Methane evaporates, rises into the atmosphere, cools, condenses, and eventually falls as rain. These methane rains are consistent enough to form lakes and rivers on Titan's surface. When examined at a more advanced level, it has been suggested that some planets may host even more extraordinary types of precipitation. According to certain theoretical models, carbon-rich planets could experience diamond rain. On such planets, under extreme pressure and temperature conditions, carbon atoms can form crystalline structures. In particular, within the deep atmospheres of planets classified as ice giants, it is believed that methane can break down, releasing carbon that then condenses into diamond form. In reality, this process is not exactly rain in the classical sense, but rather a phase transition and precipitation process occurring under high pressure. However, since solid particles move downward as a result, it is commonly referred to as diamond rain. At this point, planets in our own solar system, such as Neptune and Uranus, hold special importance. It is believed that within their dactyly structures, conditions of extremely high pressure exist where carbon can transform into diamond. Laboratory experiments have also demonstrated that such conditions can be simulated and that carbon can indeed transition into diamond form. This strengthens the possibility that there could be continuous diamond precipitation occurring deep within these planets. Perhaps centuries from now, humanity might even begin mining operations on such planets, and powerful nations and major corporations could enter a race to reach them. So what do you think? Would something like this actually be possible? And if it were, would governments keep it hidden from humanity? Because if such a scenario became reality, the value of diamonds and other minerals on Earth could drastically change, either becoming far cheaper or far more expensive. In short, the entire market could shift dramatically in one direction or the other. Don't forget to share your thoughts in the comments. And that's it, my friends. In short, every planet follows fundamentally the same precipitation system, but due to each planet's unique properties, what actually falls from the sky can be completely different. I hope you now understand that rainfall should not be underestimated or considered a simple phenomenon. It is in fact the result of a highly complex and intricate system. Unfortunately, that's all for today. If you enjoyed the video, don't forget to hit the like button, subscribe to support the channel, and share your ideas for future videos in the comments. Until we meet in the next video, take good care of yourselves. Goodbye.